Okay, so you've shared a whole stack of material with us. Articles, notes, really interesting insights, all focusing on the life and work of, well, a scientist recently called one of the world's greatest.
Hmm.
Today we're going to dive deep into all that material to really get a handle on the profound legacy of Dr. Alan G. Marshall, who sadly passed away just recently, June 6th, 2025.
That's right. And our goal for this deep dive really is to unpack who he was as a person and a scientist. And crucially, this revolutionary tool he co-invented, it's called Fourier transform ion cyclotron resonance mass spectrometry. Bit of a mouthful.
Yeah, let's just call it FTICRMS for short, maybe.
Definitely. FTICRMS. We want to understand the key scientific ideas behind it, but, in ways that make sense even if you don't have a chemistry PhD.
Right.
Explore the incredible impact it's had across so many different fields, and maybe most importantly, what his story tells us about scientific discovery itself and the power of connecting different kinds of knowledge.
Absolutely. And maybe to cut through that technical name right from the start. The easiest way I found to think about his main contribution, this FTICR-MS thing, is that he basically helped create the world's most precise weighing scale for molecules.
That's a great analogy.
Yeah, like imagine you need to figure out what's in, say, a tiny drop of crude oil,
Hmm.
or maybe a complex biological sample. These things are like chemical soups with thousands, maybe tens of thousands of different ingredients. Right?
Exactly. Incredibly complex.
And the older tools, they might tell you some things are in there, but not with much specificity. Marshall's invention gave scientists a scale so unbelievably accurate, it could not only tell you the weight of a molecule, which is already tiny, but with such precision, it could help you figure out exactly how many carbon atoms, how many hydrogen, oxygen, sulfur atoms, whatever, make up that molecule, just from its weight.
And that specific level of detail, that accuracy, it really did revolutionize our ability to analyze and understand these incredibly complex mixtures that are, well, they're everywhere in the environment, in our own bodies, you name it.
Okay, so let's start by getting a sense of the man himself, the person behind this huge invention. Based on the sources you shared, who was Alan Marshall? The scientist, but also, apparently, the gentleman. Where did his story begin?
Well, Alan George Marshall, he was born in Bluffton, Ohio, back in 1944. His academic path, it started at Northwestern University. He got his undergrad degree there in chemistry with honors in '65.
Okay.
Then he went out west to Stanford University for his PhD in physical chemistry, which he wrapped up in 1970.
And even early on, the sources mentioned he wasn't like just focused on science, right?
Petite.
He had other interests.
Yes, and that's a really key point the sources make, and it kind of foreshadows his later innovation.
Yeah.
He played the clarinet, he was on the track team, cross country too,
Wow.
and there's this great little story from high school. He was apparently neck and neck with some rival for the Outstanding Male Scholar Award. Both had top grades in science, obviously. But Marshall won because he had better grades in gym class.
No way. Gym class.
Yeah. It's just a small detail, but it really paints this picture of someone who, excelled in different areas, not just the purely academic stuff.
That breadth definitely seems like a theme. And then there's this really crucial moment early in his education that sounds almost like an accident, but it ended up shaping his entire future.
It's pretty amazing, isn't it? He first went to Northwestern planning to do medicine. He was actually in a special 6-year med program.
Right, intending to be a doctor.
Totally. But, as he later said, he figured out pretty quickly that he liked medicine but hated medical school. It wasn't the subject, apparently, but just the structure or maybe the whole environment of medical training that just didn't suit him.
Wow, that's a big realization to have early on.
Huge. And because he'd spent 3 years in this very specific program, switching wasn't straightforward. He had to change his major, but the timing meant that the only degree he could realistically finish in the 1 year he had left at Northwestern was chemistry.
So he switched to chemistry almost out of necessity.
Pretty much, yeah. It was this decision, almost forced by finding himself in the wrong program, that set him firmly on the path to chemistry, where he'd make these, massive contributions. It wasn't some lifelong dream from childhood. It was a path he kind of stumbled onto and then just ran with brilliantly.
That's fascinating. A whole career basically launched by a necessary pivot.
Mm-hmm.
So what did his professional journey look like after finishing that chemistry PhD at Stanford?
Well, he started his teaching and research career up in Canada at the University of British Columbia, UBC, in Vancouver back in 1969. And it's interesting, the sources point out that UBC kind of took a chance on him then. He didn't even have a standard postdoc position lined up when he started there.
Sounds like a bit of a pattern starting institutions, seeing potential even if the path wasn't perfectly conventional.
It does seem that way. After UBC, he moved back to the States to the Ohio State University, OSU, in 1980. He was hired there as a professor, but also to direct a brand new instrumentation center. And again, OSU hired him, even though at that time he had less external grant funding compared to maybe some other candidates, and he hadn't actually run a big facility like that before. They clearly saw the promise in his work and his ideas.
So UBC took a chance, OSU took a chance. Where did he eventually land for the longest and maybe the most impactful stretch of his career?
That was Florida State University, FSU, starting in 1993. He stayed there right up until he retired in 2024, so a really long and incredibly productive time. He was specifically recruited down there by Jack Crow.
The founder of the MagLab.
Exactly, the founding director of the National High Magnetic Field Laboratory, the MagLab, which is based at FSU. Now, Marshall was apparently hesitant about the move initially. His wife, Marilyn, she had a very successful long career going in Ohio, and moving was a big deal for them. He wasn't really looking to leave.
Makes sense. So what sealed the deal? What persuaded him to go to Florida?
Well, Crow was apparently very persuasive, but a huge factor was the opportunity to build this truly world-class program centered around extremely powerful magnets. These magnets are absolutely key for the kind of mass spectrometry he was pioneering. And there was a big carrot, a major state grant from Florida specifically earmarked to build a new state-of-the-art instrument.
Money talks, especially for big science.
It certainly helps. And, true to form, Crow and FSU also took a bit of a chance. Marshall's federal funding was actually up for competitive renewal right when he was considering the move. That could have been seen as risky for FSU, but they banked on his potential.
And his role there at FSU in the MagLab, it became massive, didn't it?
Oh, absolutely central. At FSU, he founded and then directed the Ion Cyclotron Residence Program within the MagLab from '93 right up to 2014. He also held this prestigious title, the Robert O. Lawton Professor of Chemistry and Biochemistry. And that program, it basically became the global hub for advanced FTICR MS research.
Now, the sources you shared, they don't just list his jobs and accomplishments. They give a really warm, almost personal picture of him. He keeps being described as a gentleman.
They really do paint a vivid picture, and is one of the most striking things about the materials. That MagLab article, it has this wonderful description. You can almost see him sitting back in his favorite armchair, dressed super casually, khaki shorts, jean shirt, maybe feet up, twirling a sideburn, holding a drink with a yellow koozie.
Sounds very relaxed.
Exactly. He looked totally chilled out, but the article stresses he was actually hard at work. Although apparently Marshall himself would have crossed out hard and put in enjoyable or maybe engrossing instead.
That fits perfectly with how his work ethic is described, not like a chore, but something he genuinely loved.
Totally. He was known to work 7 days a week. Not because he had to, but because, as he put it, it was the most fun thing he could think to do. The sources mentioned there wasn't really a clear line between his work and the rest of his life. His lab literally spilled over into his home. He even held his weekly group meetings there.
And he wasn't just intense about the work. He had a good sense of humor, too.
Oh, yeah, definitely. Described as cracking jokes all the time, laughing with this very distinctive, gruff, throaty laugh. Some people apparently even compared him, maybe partly visually, partly humorously, to Groucho Marx, the unruly hair and eyebrows, the mustache, always ready with a funny comment.
Groucho Marx, that's great.
But underneath that playful side, and even the intensity of the scientific debates, there was this real deep kindness.
Which brings us back to that word, gentleman.
Yes, that term comes up again and again. And the sources point out, it's a word not often invoked these days in the sciences or any other field. Chris Hendrickson, a very close colleague, is quoted saying, "It's rare to have somebody be that brilliant and that nice. It's really rare."
Wow.
And Christina Hawkinson, one of his many successful former postdocs, she also talked about how easy and supportive he was to work with. It really says a lot about the kind of atmosphere he created around him.
Those personal stories really help fill out the picture. What about his sheer brain power? His intellect?
Legendary, apparently. Described as encyclopedic, but combined with incredible insight. Christina Hawkinson tells this amazing story that really illustrates it. You could supposedly ask him about any of the hundreds of papers he published over decades, and he could instantly recall the specifics, the exact equations they used, the experimental details, the main findings. Just boom, right there.
That's incredible recall.
Astounding. That ability to just hold on to, access, and then synthesize these huge amounts of scientific information was a key part of his brilliance.
Okay, so we've got this picture now. Brilliant, kind, funny, incredibly dedicated, broad interests. Someone who found immense joy in the work itself. That foundation really helps us understand the scientific problem he was so driven to tackle.
It absolutely does. Understanding the challenge he was facing is key to appreciating why his solution was so revolutionary.
Which takes us right to that fundamental problem. Why was it so important, so critical to be able to weigh molecules with extreme precision?
Well, at its heart, analytical chemistry is all about finding out what molecules are in a sample, and often how much of each there is. Think about analyzing a new drug, or studying metabolites in blood, or checking for pollutants in water. You need to identify the chemical ingredients.
Right, like trying to figure out that complex soup we mentioned earlier.
Exactly that analogy the sources use. Imagine a soup, but instead of carrots and potatoes, it has thousands, maybe tens of thousands of different invisible ingredients all mixed up. To really know what's in that soup, you need a way to identify every single ingredient without being able to see it or, taste it.
And mass spectrometry, that's the tool that does this by weighing the molecules, right?
Precisely. Mass spectrometry works by separating and detecting molecules based on their mass-to-charge ratio. So fundamentally, it's a way of weighing molecules.
Okay, so mass spec weighs molecules. But why was getting extreme precision in that weighing process the big hurdle? What were the limits of the older methods?
This is the crucial bottleneck Marshall's work addressed. Think about that soup again. If your scale isn't very precise, like the older mass spec techniques often where lots of different ingredients might have weights that are just too similar for your scale to tell them apart.
They all kind of blur together.
Exactly, their signals overlap. The sources describe this limitation as giving you a blurry and incomplete picture of what's really in your sample. You might know there's something in a certain weight range, but you couldn't definitively say which specific molecule it was if several possibilities had very similar weights that fell within that blurry range.
So it's like having a scale that can tell an apple from an orange, sure, but maybe not a Granny Smith apple from a Fuji apple if they happen to weigh almost the same.
That's a really good way to think about it. You lose the ability to pinpoint specific components when things get complex. And this is the key, if your mass spectrometer is extraordinarily precise, if it has what scientists call high mass accuracy and high resolution terms the sources emphasize,
Then you can tell the difference.
then you can distinguish each and every ingredient, even if their weights differ by only the tiniest fraction. You get sharp, distinct signals instead of blurry lumps.
And that incredible precision, it unlocks something even more powerful than just telling similar molecules apart.
It really does. The sources explain that if your mass measurement is accurate enough, you can actually figure out the exact elemental composition of an unknown molecule just from that measured mass.
How does that work?
Because different isotopes of elements, like, say, the common carbon-12 versus the slightly heavier carbon-13, have very slightly different masses. If your measurement is precise enough to detect these tiny differences, you can essentially calculate the exact number of carbons, hydrogens, oxygens, nitrogens, sulfurs, etc. that must be in that molecule to add up to the exact mass you measured.
Wow. So you're basically getting the molecular formula, the exact recipe, just by weighing it accurately enough.
That's the power of it. It was the difference between having a vague idea of what might be in your sample versus knowing the precise molecular formula for potentially thousands of different components all at the same time.
That is genuinely transformative for understanding anything complex chemically.
Absolutely. It was the key to unlocking incredibly complex systems.
Okay, so the goal was clear. Build a much, much better molecular scale.
Yeah.
But as you mentioned, Marshall's genius wasn't necessarily in inventing every single piece from absolute scratch. It was more about combining existing ideas in a completely new and powerful way.
That's right.
So let's break down those building blocks. This brings us to understanding, in simple terms, nuclear magnetic resonance, NMR, ion cyclotron resonance, ICR, and this mathematical tool, the Fourier transform, FT.
Right. So Marshall had deep expertise stemming from a couple of distinct areas. One of those was nuclear magnetic resonance, NMR.
This was something he got into early on during his PhD, correct?
Yes, exactly. It was actually central to his PhD research at Stanford. As he mentioned himself, his thesis work involved using NMR techniques to study how drug molecules bind to receptors in the body. Now, interestingly, he ultimately moved away from that specific biological application. It didn't quite ignite his long-term passion, apparently, but that early work gave him absolutely crucial, hands-on, deep expertise in NMR. He knew the techniques, the instrumentation, and the underlying physics and mathematics inside out.
Okay, so deep MR knowledge. How does that connect to one of the key ingredients in his later invention, the Fourier transform?
Ah, this is the vital link. The sources point out that around that time, this powerful mathematical algorithm, the Fourier transform, had recently been successfully applied to NMR technology.
What did it do for NMR?
It basically allowed NMR scientists to collect their data much, much faster and more efficiently. Instead of scanning through frequencies one by one, they could excite everything at once and use FT to sort out the signals. In fact, a Swiss scientist, Richard Ernst, later won a Nobel Prize, partly for his work on developing this Fourier transform NMR.
So Marshall, with his NMR background, would have been right on top of this cutting-edge development.
Exactly. He was keenly aware of this powerful mathematical tool and how it was transforming his original field of expertise, NMR.
Okay, so that's one piece. Deep NMR knowledge, plus awareness of FT's power there. What was the second main technical area he was involved in?
That was ion cyclotron resonance, or ICR. Now, unlike FT-NMR, which was relatively new, ICR was a technique that had actually been around for quite a while. It was first developed way back in the 1930s.
Okay, so an older technique. How does ICR work? Can we break that down simply?
Sure. At its most basic, ICR involves taking molecules that have an electrical charge, we call them ions, and putting them inside a very strong magnetic field. Now, when a charged particle, an ion, moves into a magnetic field, it doesn't just keep going straight. The field exerts a force on it, forcing it to move in a circular path. So, in an ICR instrument, these ions get trapped by the magnetic field and they start orbiting or rotating, that's the cyclotron part, around the magnetic field lines.
Okay, so they're captured and spinning around in circles inside the magnet.
Exactly. And here's the absolutely crucial principle. The frequency at which an ion rotates, how fast it spins around in that circle, is directly and very precisely related to its mass, or more accurately, its mass-to-charge ratio.
Ah, so heavier ions spin slower, lighter ions spin faster.
Precisely. A heavier ion takes longer to complete an orbit in the same magnetic field compared to a lighter ion.
So if you can measure that rotation frequency, you can figure out the molecule's mass. It's another way to get that molecular weight information.
That's exactly right. And older ICR techniques could indeed measure these frequencies and determine masses, but they had significant limitations. They were often quite slow, sometimes requiring the instrument to be tuned to detect ions of only one specific mass at a time. You'd have to scan through the masses. And the resolution, the ability to separate ions of very similar mass, wasn't always as high as needed for really complex mixtures.
Okay. Slow and maybe not sharp enough for complex stuff. Which brings us neatly to the third piece, the Fourier transform, FT. We heard it was revolutionizing NMR. What exactly is this mathematical tool, in simple terms, and what magic did it bring?
Right. Think of the Fourier transform, FT, as less of a physical thing and more of a powerful mathematical lens or algorithm. Its job in this context is to take a really complex signal that's changing over time. Imagine the combined electrical signal produced by thousands of different ions all spinning around at their own unique frequencies inside the ICR cell simultaneously and mathematically decompose it, break it down into all the individual frequencies that make it up.
So it untangles the messy combined signal.
Exactly. It converts that jumbled signal, evolving over time, into a much clearer picture, a spectrum, which is essentially a graph.
What does that spectrum show you?
It plots out all the different frequencies that were present in that original signal. And since we know frequency corresponds directly to mass in ICR, this spectrum effectively shows you all the different masses present in your sample. You see peaks on the graph at specific mass values, telling you which molecules are there. And the height or intensity of each peak tells you roughly how much of that molecule you have compared to the others.
It's kind of like taking a recording of a whole orchestra, playing a complex chord, and then using FT to mathematically figure out exactly which instruments were playing which notes and how loudly each one was playing.
That's a fantastic analogy. That's precisely what it does for the mixed ion signals.
And the mathematical advantage. The sources mention something about making math easier.
Yeah, it essentially provides a mathematical shortcut. The source mentions it converts integrals into multiplication and division. We don't need the nitty-gritty math, But the key takeaway is that FT made the complex task of analyzing the combined signal from all the ions at once computationally feasible and, crucially, very fast.
Okay, so this is the game changer. Older ICR methods might have had to measure one frequency, one mass at a time, which was slow. But the Fourier transform allowed scientists to capture the signal from all the different ions rotating in the magnetic field simultaneously, and then use math to sort them all out afterwards.
Precisely. That's the core benefit FT brought. It enabled simultaneous detection of everything in the sample, leading to a massive improvement in both speed and sensitivity, because you're collecting data on all your molecules for the entire measurement time, not just scanning past them one by one.
Okay, the pieces are on the table now. Marshall had this deep background in NMR, where FT was already making waves. He also had a strong grasp of ICR, this older technique for weighing ions based on rotation frequency. The pieces were there. Which leads us straight to the aha moment, the birth of FT-ICR-MS. How did he connect these seemingly separate dots?
This is really where Marshall's unique background was absolutely essential. He wasn't just an NMR expert or just an ICR expert. He had serious knowledge and experience in both, combined with that broad scientific curiosity we talked about. The stroke of genius wasn't inventing, say, a brand new type of magnet or a totally new way to detect ions. It was the fundamental realization, the insight that this powerful mathematical tool, the Fourier transform, which was already proving its worth in processing NMR signals, could be applied directly to the signals generated by ions rotating in an ICR cell.
And that applying FT there would have the same kind of benefits.
Yes. He saw that it could dramatically improve both the speed of the measurement by detecting all ions at once and the resolution, the ability to distinguish very similar masses, because the FT method allows for very precise frequency determination from the time domain signal.
So he basically saw that the underlying mathematical principle, the FT, wasn't specific to NMR. It was a fundamental signal processing tool that could be transferred from one scientific domain, NMR, to another, ICR, which hadn't yet benefited from it. This feels like a really core lesson about innovation itself, doesn't it?
It absolutely is. This ability to look past the surface differences between scientific fields, different experiments, different jargon, and recognize the shared underlying principles or the applicability of powerful tools like mathematical algorithms, that's often where the biggest breakthroughs happen. It really speaks to that idea the sources mention of being an explorer who is well and broadly read, somebody who can spot those unexpected connections.
And did he keep this idea to himself initially?
No, not at all. He immediately took the idea to his friend and colleague there at UBC, Mel Commisaro. Commisaro was the real hands-on expert when it came to the experimental hardware and practical aspects of ICR at the time.
Okay, so he needed Commisaro's expertise to actually build it. What was Commisaro's first reaction?
Well, Marshall later recalled that Commisaro was actually pretty skeptical at first. He apparently came up with a list of reasons why he thought applying FT to ICR signals wouldn't work, or why it would be technically too challenging to implement.
The classic expert skepticism.
Right. But Marshall, with his deep understanding of both techniques and his strong conviction about the potential, was able to talk him through the objections and ultimately convince him that it was not only possible, but potentially revolutionary.
That moment, convincing the skeptical expert who knew the practical hurdles intimately, that really highlights the importance of their collaboration. This wasn't just a solo flash of genius.
Marshall always stressed that point. He explicitly said it wasn't accidental that it took two people. Commisaro brought that essential, deep expertise in the practicalities of building and running the ICR experiment. Marshall brought strong ICR knowledge too, but also that crucial understanding of NMR, and, critically, how the Fourier transform had already been successfully integrated there. It was the synergy, the combination of their complementary skills and knowledge that allowed them to actually design, build, and successfully test the concept.
So it really required that unique blend of different but related expertise, plus, as the sources mentioned, Marshall's confidence in the idea, his ability to work as a team, and just plain diligence.
Exactly. The sources point specifically to his broad command of science, spanning both NMR and ICR, his self-assured confidence that the idea would work, his gift for effective teamwork with Commisaro, and then just the sheer hard graft required to put in the long hours and do the tedious calculations needed to turn the theoretical concept into a working experiment.
And the moment they knew it had worked, that first successful experiment. Can you describe that?
That pivotal moment happened on December 17th, 1973. They were using a 2 Tesla magnet, which is pretty modest compared to the mag lab giants today, but it was what Commisaro had skillfully configured into what became the world's first functioning FTICR mass spectrometer. Marshall was apparently absolutely ecstatic when he saw the first decent spectrum come out. He immediately grabbed the piece of chart paper with the data and went running down the hall to find his friend Naresh Dalal, who was working late in another lab.
Wow, imagine that moment. What did I say to Dalal?
Bursting with excitement, he essentially waved the paper at him and said something like, "Look, we just created a new technique." And then with characteristic confidence, he declared, "This is the world's best mass spectrum."
The world's best mass spectrum. Quite a claim for the very first result. So, based on the sources, what actually made that initial spectrum, generated by this brand new FTICR method, arguably the world's best at that specific moment? What were the immediate, obvious breakthroughs?
There were two huge things immediately apparent. First, the resolution was simply unprecedented for ICR at the time. The sources describe the peaks on that first spectrum as being very narrow. What that means in practice is that they could clearly separate and distinguish different molecules whose masses were incredibly close together. Something older techniques just couldn't resolve. They'd just show up as one blurry peak. Even in that very first experiment back in '73, they were able to clearly identify and separate 50 distinct peaks, representing 50 different chemical compounds, all present in the sample mixture at the same time.
Okay, going from a blurry picture to clearly seeing 50 individual components at once. That alone is revolutionary resolution.
Absolutely. And the second massive advantage was the incredible speed. Getting that detailed high-resolution spectrum showing all 50 compounds took just a few seconds. The sources contrast this dramatically with the older traditional ICR methods where you had to slowly scan through the masses one by one. That process could easily take an hour or more just to get a much less detailed, lower-resolution spectrum of the entire sample.
Yeah.
Measuring everything simultaneously using the power of the Fourier transform was just a monumental leap forward in efficiency.
So, revolutionary speed and resolution achieved by cleverly combining existing ideas with this powerful mathematical tool. But despite how clear the breakthrough seems in retrospect, the sources mentioned there were initial challenges getting it recognized. Some skepticism.
Yes, it's almost hard to believe now, but their initial paper describing these groundbreaking results was actually rejected by a major prestigious journal in the field, the International Journal of Mass Spectrometry and Ion Processes.
Rejected? What?
The reason given, essentially, was that the reviewers or editors just didn't really look like it was going to amount to anything. They didn't grasp the significance or the potential impact of what Marshall and Commisaro had achieved.
That's just astonishing. A technique that would completely transform the field being dismissed like that initially.
It really highlights how sometimes truly disruptive innovations, things that break the existing mold, aren't immediately understood or embraced by the established community. Fortunately, another journal, Chemical Physics Letters, did recognize the importance and accepted the paper. And that publication went on to be cited thousands upon thousands of times, becoming a cornerstone of the entire field. But yeah, Marshall was understandably frustrated by that initial rejection. His belief in the technique, however, was rock solid.
He just felt deep down that it had to work.
He did. He's quoted saying, "I felt like it had to work." But he also acknowledged realistically that it took a while to convince everybody else. And crucially, he didn't just publish that first paper and move on. He dedicated the rest of his career to continuously developing, refining, and improving the technique over decades. He patiently worked, waiting for the necessary enabling technologies like bigger, stronger magnets and much more sophisticated electronics to become available, and also for the broader scientific community's understanding to catch up to the immense potential he had seen back in 1973. As his wife, Marilyn, shrewdly observed, "Smart isn't enough. He's also diligent." That persistence, that sheer diligence over the long haul, was arguably just as critical as the initial spark of genius.
That long-term dedication, not just inventing it, but nurturing it, refining it, advocating for it, that's such a key part of his legacy, isn't it?
It absolutely is. He didn't just publish a paper and walk away. He fundamentally built the field around his invention.
Which leads us perfectly into thinking about how he did that, how he kept pushing the boundaries after that initial invention at UBC. This takes us to Section 5, building the field and really pushing the boundaries. What came next in the evolution of FTICR-MS?
Well, his move to Ohio State University in 1980 was a key step. It gave him a new platform, more resources to really push the development forward. A really significant milestone there came in 1983 when he secured a major grant from the NIH, the National Institutes of Health, specifically to build a 3 Tesla FTICR instrument.
Okay, bigger magnet than the first one.
Yeah, 3 Tesla was pretty state-of-the-art for FTICR back then, and having that instrument allowed him to really demonstrate the technique's growing power and potential to a much wider scientific audience. It was also while he was at OSU that he developed a really important related technique called SWIFT, that stands for Stored Waveform Inverse Fourier Transform. It became a widely used method for selecting and manipulating specific ions within the FTICR cell, adding more experimental flexibility. He was definitely successful in attracting more funding and top researchers to OSU during that period, really showing the growing momentum behind his invention.
And then there was this other development external to his own lab in the late 80s that apparently gave FTICR-MS a massive boost, especially for studying biological molecules.
Yes, that was absolutely pivotal. In 1988, John Fenn developed a technique called electrospray ionization, or ESI. Fenn actually shared a Nobel Prize for this later on. The big problem before ESI was figuring out how to get large, often fragile biological molecules, things like proteins, big peptides, into the gas phase, as ions so they could be analyzed by mass spectrometry without completely destroying them in the process.
Like they're delicate.
Exactly. ESI provided this incredibly gentle, effective way to take these big biomolecules that were dissolved in liquid and turn them into ions flying around in the vacuum of the mass spectrometer, ready to be analyzed.
So ESI essentially unlocked the door for FTICR-MS to analyze this whole world of huge biological molecules that were previously inaccessible.
That's precisely it. Marshall himself said, reflecting back, that's when the growth really took off for FTICR-MS in the biological sciences. Suddenly, it became this indispensable tool for fields like proteomics, studying all the proteins in a cell, for pharmaceutical research especially, understanding how potential drug molecules bind to protein targets, and for many other areas of biotechnology.
And then came the move that really cemented his program's world leadership, heading down to FSU and the Mag Lab in 1993.
Right. That move was fundamentally driven by the allure of working with even more powerful magnetic fields. Jack Crow, as we mentioned, successfully recruited him, and a major part of that recruitment package was that state grant from Florida to build a brand new 9.4 Tesla FTICR instrument. At the time it came online, that was the biggest, most powerful magnet dedicated to FTICR anywhere in the world.
Wow. So going from the initial 2 Tesla, then 3 Tesla at OSU, now jumping up to 9.4 Tesla, the magnetic field strength just kept climbing.
And that increasing field strength is absolutely critical. Higher magnetic fields in FTICR directly translate to achieving even higher resolution, sharper peaks, better separation of similar masses, and also better sensitivity and mass accuracy. At the Mag Lab, Marshall really built his program into the undisputed international center of excellence for this technique. The sources highlight his incredible success in securing funding, noting he was directly responsible for bringing in over $20 million in external grants, including significant support from industry, particularly oil companies who saw the value.
And scientists from all over came to use these instruments.
Absolutely. Researchers from literally around the globe traveled to the Mag Lab specifically to use their unique high-field FTICR instruments and to collaborate with Marshall's team, tackling problems that simply couldn't be solved anywhere else.
And the evolution of the magnets themselves at the Mag Lab became quite a story, didn't it? It didn't stop at 9.4 Tesla.
Not at all. Building on that initial 9.4 Tesla system, they later added another one, then pushed the boundary further with a 14.5 Tesla instrument, then a 15 Tesla. And just last year, in 2024, they officially opened a phenomenal 21 Tesla magnet system. That currently represents the highest magnetic field strength available for FTICR research anywhere on the planet.
21 Tesla. That's incredible power.
It is. And the sources rightly emphasize it's not just about having the biggest magnet. It's about the incredibly sophisticated integration of that magnet with all the other stuff that goes into the spectrometer, the advanced electronics needed to handle the signals, the highly optimized ion optics to get the ions into and out of the cell efficiently, the sensitive detection systems. Marshall and his team were constantly innovating and improving all these components over decades to fully exploit the potential of those powerful magnetic fields.
And Marshall himself, he wasn't content to just sit in the lab building instruments. He became this tireless advocate, almost a missionary, as the sources put it, for the technique itself.
Yeah. He absolutely was. He deeply understood that the power of this tool wasn't useful unless the wider scientific community knew about it, understood its capabilities, and could access it. The sources report he gave something like over 1,400 talks and presentations all over the world during his career.
Wow, 1,400 talks.
Yeah, explaining FTICR-MS and what it could do, not just to other chemists, but to biologists, environmental scientists, material scientists, even to people outside of traditional science fields. He actively encouraged researchers everywhere to send their most challenging, complex samples to the Mag Lab, essentially saying, let us show you what FTICR-MS can reveal that your current techniques might be missing.
He was constantly on the lookout for new territory to conquer with the technique, new problems to solve.
That was absolutely his mindset. And his mission, as he saw it, was bigger than just generating publications from his own lab group. It was about building the entire field of FTICR-MS globally. He explicitly aimed to, as he sometimes put it, infect visiting researchers with enthusiasm for the technique, demonstrate its power on their own samples, and then strongly encourage them to go back to their home institutions and acquire their own FTICR instruments to continue pushing the boundaries on their own research problems. He really embraced the role of building the field as a core part of his mission, leading a national user facility.
That ability to combine that deep scientific rigor and innovation with that kind of outward-looking advocacy and field building, it seems like a really rare and potent combination.
It really is. And his personality clearly helped. That blend of undeniable expertise, genuine charm, and easy kind of self-effacing confidence, it made him an incredibly effective communicator and ambassador for the technique. Even small, memorable things like the Australian bush hat he apparently always wore when outdoors added this touch of unique, recognizable panache.
Okay, so we have this revolutionary invention, decades of continuous development and refinement, and this global effort to disseminate the technology and build a whole community around it. This clearly points to an absolutely enormous scientific impact across many areas.
Truly revolutionary is not too strong a word.
So let's dig into that impact in a bit more detail. What exactly has this much better scale allowed scientists to finally measure? What are some of the most wide-ranging and maybe fascinating applications of FTICR-MS that are mentioned in the sources today?
Well, the sources are unanimous on this. FTICR-MS is just an extremely powerful tool that brought about nothing short of a revolution in analytical chemistry. And the fundamental reason for that revolution, as we've discussed, is that unique combination it offers. Ultra-high resolution coupled with incredibly high mass accuracy.
And just to remind ourselves, why is that combination so impactful in practice?
Because, again, that high resolution means it's just very good at telling molecules apart by mass, even when there is not much difference between them. You can pick out the individual trees in a very dense forest. And that high mass accuracy, the ability to measure the mass so precisely, is what allows scientists to determine the exact elemental composition, the molecular formula, of each of those molecules they detect. This level of fine-grained detail means scientists can finally identify, characterize, and understand the individual components within incredibly complex mixtures, things that were essentially just an unanalyzable mess before.
Okay, let's get concrete. The sources mentioned some really fascinating specific examples. Analyzing crude oil, for instance, seems like a major one.
Yes, this is probably one of the most famous and impactful applications that really showcase the power of Marshall's technique early on. Crude oil, as we know, is often described as maybe the most complicated chemical mixture known to science. Just this incredibly dense soup containing tens of thousands, maybe even hundreds of thousands of different organic compounds. Before FTICR-MS came along, getting a detailed chemical breakdown of crude oil was considered virtually impossible. It was just too complex for older analytical methods. Marshall's team at the Mag Lab applied their high-field FTICR instruments to crude oil samples, and they absolutely shattered previous records. They set a world record for the sheer number of distinct chemical compounds identified and characterized in a single sample of crude oil, revealing its true, staggering molecular complexity for the first time.
Going from virtually impossible to setting a world record for identification. That's about as clear a demonstration of a technique's power as you can get.
It really is. And this pioneering work was absolutely fundamental in establishing and growing this whole new field called petroleomics, the detailed molecular study of petroleum. Understanding the precise chemical makeup of crude oil at that level has huge practical implications. It helps the energy industry locate new oil deposits more effectively, optimize their drilling strategies, and, crucially, refine the crude oil into gasoline and other products much more efficiently and cleanly because they know exactly what molecules they're starting with.
And the value was so obvious that industry actually helped fund the science.
Yes, the potential benefits were so clear that major oil companies became significant financial contributors to building some of the powerful magnets at the Mag Lab, like the 14.5 Tesla system, specifically to advance this petroleomics research. It's a great example of fundamental science leading directly to industrial application and support.
That's fascinating. What about applications that are literally out of this world? The sources mentioned extraterrestrial samples.
Yeah, that's another really cool area. FTICR-MS, with its ability to analyze tiny amounts of complex organic material with incredible precision, has been used to study extraterrestrial samples. Researchers have employed the technique to examine the complex organic mixtures that have been isolated from things like moon dust brought back by Apollo missions and from meteorites that have landed on Earth. It's helping us understand the kinds of chemical building blocks for life, or precursors to life, that might exist beyond our own planet.
That's incredible. Taking this super precise molecular scale and applying it to dust from the moon or rocks from space. What about closer to home, in medicine and biotechnology?
Right, as we touched on earlier when talking about the impact of electrospray ionization, ESI, FTICR-MS is now a powerhouse tool in analyzing complex biological samples. For example, it's widely used in the pharmaceutical industry for studying exactly how potential new drug molecules bind to their target proteins in the body. Understanding that interaction at a molecular level is absolutely essential for designing effective and safe medicines.
And potential future uses in medicine.
The sources definitely point towards exciting future applications. One major area is the search for biological biomarkers. These are specific molecules, maybe proteins or metabolites, that you could detect in easily accessible samples like blood or urine, whose levels might change in characteristic ways, indicating the presence or progression of a disease, maybe like Alzheimer's or certain types of kidney disease, long before clinical symptoms appear. Identifying such biomarkers using the sensitivity and precision of FTICR-MS could lead to much earlier diagnosis and also give us a better molecular understanding of how these diseases develop.
That could be truly life-changing for millions. And there was even a mention of using it in security applications.
Yes, the technique's ability to provide a highly specific chemical fingerprint for complex substances makes it potentially valuable in security and defense contexts. For instance, it could be used for identifying the precise composition of unknown chemical samples, potentially including pinpointing components used in chemical or biological warfare agents as part of counterterrorism, intelligence, and verification efforts.
It really is an astonishingly versatile tool, impacting everything from energy to space exploration to health to security. And the sheer growth in its analytical power over Marshall's career is just mind-boggling.
It really is staggering when you think about it. In that very first groundbreaking experiment back in 1973, being able to clearly identify 50 different compounds simultaneously in a mixture was hailed as a massive leap forward, revolutionary at the time.
Right, 50 was amazing then.
Today, thanks in very large part to the continuous development work led by Marshall and his colleagues, pushing the magnets, the electronics, the software, modern FTICR-MS instruments can routinely identify as many as 50,000 distinct chemical compounds in a single analysis of a complex mixture like petroleum or a biological extract.
From 50 compounds to 50,000 compounds.
Yeah.
That's a 1,000-fold increase in the complexity they can unravel within one scientific lifetime.
It's an absolutely incredible illustration of the continuous pushing of scientific and technological boundaries that Marshall really championed throughout his career. And the technique isn't just some exotic research tool anymore. It's become a standard, albeit high-end, instrument in many advanced analytical laboratories around the world. The sources report that there are now over 700 FTICR mass spectrometers operating globally, making important discoveries in diverse fields every single day.
And that quote from one of his colleagues putting its significance into perspective.
Yes, that was Michael Bowers, a chemist at UC Santa Barbara. He didn't pull any punches in his assessment. He stated that Marshall's invention, FTICR-MS, is certainly in the top quarter of all things ever done in science, and probably in the top 10 to 15%.
Top 10 to 15% of all things ever done in science. That's putting it right up there with the most fundamental breakthroughs in scientific history.
It's a pretty stunning assessment from a respected peer in the field, reflecting the truly transformative impact of the technique.
Now, beyond the invention itself, beyond the world records and the global impact on science and technology, the sources you shared place just as much emphasis, if not more, on Dr. Marshall's impact on people, the students, the postdocs, the colleagues he worked with over the years. That brings us to a really crucial part of his legacy, his dedication to mentorship and service.
Yes, and this aspect of his story is perhaps just as significant, just as lasting, as the scientific invention itself. Marshall was apparently incredibly dedicated to nurturing and promoting the next generation of scientists. Over his long career, the sources estimate he mentored well over 150 PhD students and postdoctoral researchers who passed through his lab. He's consistently described as being a tireless champion for them.
What did that championship look like in practice? How did he demonstrate that support?
The sources give us a really concrete sense of his extraordinary commitment. It's mentioned that he would devote dozens of hours every single month, specifically to activities aimed at supporting his students and postdocs' careers long after they might have left his lab. This wasn't just, signing off on a standard form letter. It meant meticulously crafting hundreds of letters of recommendation, often highly personalized and detailed. And he put enormous effort into preparing compelling award nominations to help his mentees gain recognition and advance in their own careers. It was clearly a deep, genuine, ongoing commitment to their future success.
And there's that particularly touching anecdote that he himself apparently found most gratifying.
Yes, it's mentioned that what perhaps pleased him most personally was the fact that several of his former mentees, at least 5 of them by the time the article was written, had chosen to name their sons Alan. That level of personal impact, where someone feels such deep respect, affection, and gratitude that they choose to name their own child after their mentor, that speaks volumes, far beyond publications or citations, about the kind of relationship he built with the people he trained.
We also have some specific stories in the sources that really illustrate his mentorship in action.
We do. Christina Hawkinson, who we mentioned earlier and is now a very successful chemistry professor herself, shared how Marshall recognized her potential very early on when she was still figuring out her direction. He actively recruited her to come work with him as a postdoc. Then later, when she was finishing up her time in his lab and starting to look for faculty positions, he strongly encouraged her to consider opportunities in the U.S. She's originally from Sweden, and apparently actively used his network and influence to help pave the way for her successful academic career trajectory here.
That's wonderful. And Naresh Dalal, the friend who was there on the night of that very first successful experiment back in '73?
Dalal's story is another really powerful example of Marshall's long-term impact. Dalal was just a graduate student at UBC when he happened to take Marshall's class on magnetic resonance. He said that class was so inspiring, so clearly taught, that it caused him to completely change his own research focus. He switched from photoelectron spectroscopy to magnetic resonance, the field where he himself went on to become a leader. And then, years later, it was Marshall who recruited Dalal to leave West Virginia University and join the chemistry department at FSU, bringing them back together again as colleagues. Dalal considered Marshall his teacher, friend, mentor, and spoke of always feeling a feeling of awe towards him, even after decades of friendship.
And what about his interaction style during those apparently legendary weekly lab group meetings held at his home? It sounds like he could be quite intense, interrogating students like a seasoned trial lawyer.
Yes, the MacLab article paints a wonderful picture of those meetings. When students or postdocs were presenting their latest results or research plans, he would indeed question them rigorously. He'd press them hard on the details, probe for potential flaws in their experimental design or their interpretation of the data, really looking for any holes in their scientific reasoning.
Sounds tough.
It could be demanding, for sure. But the absolutely crucial detail, stressed by those who were there, is that this intense questioning was always done with a twinkle in his eye, often accompanied by a smile or a joke. He'd crack jokes, punctuated by that distinctive gruff laugh. Apparently, his questions became most pointed when students were presenting new applications of FTICR to different scientific problems. He would push them relentlessly to articulate precisely why FTICR was the best, or maybe the only, tool suitable for answering that specific scientific question. In effect, he was constantly making them defend the intelligent and appropriate application of the very technique he had co-invented and championed.
So incredibly rigorous and demanding, pushing them to think deeply, but never in a way that was intimidating, demeaning, or discouraging.
Exactly. The sources explicitly emphasize that despite the intensity of his scientific questioning, he never unduly pressured his lab members, he was never angry or punitive, and he never criticized them unnecessarily. And the observation from his group was that this very specific approach, high expectations, combined with genuine support and humor, actually, quote, substantially improves the lab atmosphere and increases productivity. Students felt challenged to do their absolute best work and think critically, but they weren't afraid to present preliminary data, admit when they didn't know something, or ask tough questions themselves. He fostered an environment of intellectual rigor combined with psychological safety.
And this ethic of service, of supporting others, it extended beyond just his direct research group, didn't it?
It absolutely did. He was known for consistently going more than his share to support the broader chemistry department at FSU, the overall mission of the MagLab as a national user facility serving scientists from everywhere, and the individual careers of his staff members, not just the students and postdocs. This involved things like diligently attending countless committee meetings, writing endless letters of support for colleagues and programs, making phone calls on behalf of others, basically doing whatever administrative or service work was needed to support the institutional mission and help the people around him succeed. His wife, Marilyn, described him as having a true servant's heart when it came to his profession and his institutions.
And it sounds like that profound willingness to support others, to take chances on people, was maybe influenced by the support and chances he himself received early in his own career.
Absolutely. The sources suggest he never forgot the mentors who encouraged him way back, like his eighth grade science teacher or his freshman physics professor at Northwestern. He actually dedicated his PhD thesis to that professor. And he clearly deeply appreciated the fact that institutions like UBC, OSU, and Jack Crow at the Mag Lab had taken a chance on him at crucial junctures when his path wasn't conventional or his funding wasn't guaranteed. He understood firsthand the immense value of someone believing in your potential and giving you an opportunity, and he made it a point throughout his career to pay that forward, to provide those same kinds of opportunities and that same kind of steadfast support for others.
So his legacy really is twofold, isn't it? There's the monumental invention itself, the FTICR-MS technique that transformed analytical chemistry worldwide and is still making discoveries today. And then there's this equally profound human legacy, embodied in the generations of scientists whose careers and maybe even lives he fundamentally shaped through his mentorship and support.
A truly powerful combination of lasting scientific impact and profound human influence.
That brings us perfectly to our conclusion then, pulling all these different threads together. When we look back at Alan Marshall's whole story, what does it tell us about the true measure of innovation? And what's the core lesson here, drawing specifically from the conclusion of that primary source you provided?
The primary source really nails this in its concluding thoughts, I think. It argues very persuasively that true game-changing scientific advancement often doesn't come from just digging deeper and deeper within one extremely narrow specialized field. Instead, it frequently emerges from the fusion, the creative combination of ideas, concepts, and tools that actually originate in seemingly separate, sometimes quite disparate scientific domains.
It's about having the vision to see the connections that others might miss, recognizing some kind of shared essence or underlying principle that links different fields.
Exactly. The sources use this wonderful phrase describing the innovator as an explorer who is well and broadly read. It's someone whose curiosity, whose knowledge base, isn't confined by the traditional, often artificial boundaries we draw between disciplines. This kind of individual can look past the surface-level differences, the different jargon, the different experimental setups, and grasp the fundamental principles or the powerful tools, like a mathematical algorithm, that could be incredibly transformative if they were just applied in a new context.
And Alan Marshall's journey with FTICR-MS is just a perfect textbook case study of exactly this principle in action.
It really is. Think about it. His somewhat unusual academic path gave him deep, practical, hands-on expertise in both nuclear magnetic resonance, NMR, and ion cyclotron resonance, ICR. These were considered distinct techniques, often practiced by different communities, but he had mastered the intricacies of both. And crucially, he was also right there at the forefront, keenly aware of how this powerful mathematical tool, the Fourier transform, was just beginning to revolutionize data analysis over in the NMR world.
So his breakthrough insight wasn't inventing FT or inventing ICR, but seeing the link.
Precisely. His stroke of genius was realizing that this same fundamental mathematical principle, the Fourier transform, wasn't inherently tied only to NMR signals. He saw that it could be transferred, transplanted, and applied directly to the time domain signals generated by ions rotating in an ICR experiment to achieve the same kinds of dramatic improvements in speed, sensitivity, and especially resolution that were transforming NMR. He effectively took a tool from one domain where it was just starting to flourish and applied it to solve a major bottleneck in another domain where its potential hadn't yet been recognized.
He created a technique that, as the sources note, was initially non-obvious to many in the field, precisely because it required bridging these different areas of knowledge, these different ways of thinking. But in doing so, he created this incredibly powerful new capability, this tool that has since empowered thousands upon thousands of scientists worldwide to ask and answer questions about the molecular world, from oil to diseases to outer space, in ways that were simply impossible before.
It was fundamentally about finding, as you put it so well right at the start, a better way to measure the world. And he found it not by inventing something entirely new out of whole cloth, but by intelligently, creatively combining disparate pieces of existing knowledge. And his legacy, therefore, it isn't just captured in the hundreds of FTICR instruments operating globally today, or even just in the countless discoveries made with them, as monumental as those are. It's also woven into the careers and the scientific DNA of the hundreds of scientists he trained and inspired. He showed them by his own example that it's possible to be both a true giant in a field, someone who fundamentally reshapes the scientific landscape, and a true gentleman, someone known for their kindness, their supportiveness, their generosity with their time and their knowledge. He embodied being both a revolutionary inventor and a dedicated, humane mentor.
And even the choice his family made for memorial donations, mentioned in the sources the Nature Conservancy or the National Audubon Society, that feels like a really fitting, almost poetic echo of his life's work, doesn't it?
It really does seem fitting. His entire scientific career was dedicated to developing and using this incredibly precise tool to meticulously reveal the intricate, the complex, the often beautiful molecular reality that underlies the natural world all around us. So, supporting organizations whose mission is to protect that natural world seems like a very thoughtful and resonant way to honor his lifelong curiosity and his immense contributions to understanding it, molecule by molecule.
There's just a truly inspiring story all around about the power of intellect, yes, but also curiosity, the willingness to cross disciplinary boundaries, and the profound impact of combining that with kindness and mentorship.
A powerful reminder, I think, of what becomes possible when you manage to combine that deep scientific rigor and creativity with a genuinely generous spirit and a mind that's open and broad.
So, as we wrap up this deep dive today, the key takeaway that really resonates for me, and hopefully for you listening, is the immense power of intellectual curiosity that refuses to stay in just one box. The power of cultivating broad interests, and crucially, developing that ability to connect seemingly unrelated ideas or techniques. That seems to be a potent force for real innovation, whether you happen to be working in science or maybe in business or the arts, or really any field where complex problems need solving.
Marshall's story is just such a compelling testament to that core principle that being well and broadly read, being intellectually adventurous, can lead you to insights and breakthroughs that might remain completely invisible if you just stay confined within the comfortable boundaries of a single narrow specialty.
And perhaps the most exciting part is that despite all the incredible discoveries already made using FTICR-MS over the past 50 years, the sources strongly suggest that this story is far from over. Marshall himself, even as he approached retirement, apparently felt his best stuff may be ahead of him. And colleagues like Naresh Dalal voiced the feeling that the impact we've seen so far might just be the tip of the iceberg, especially as the technology continues to evolve with even bigger magnets on the horizon, even better electronics, new ways to couple FTICR with other techniques.
That's a really exciting prospect, isn't it? That the full potential of this powerful tool, itself born from connecting different fields, is maybe still unfolding, still waiting to be fully realized.
It definitely makes you wonder, what profound new insights about our world, maybe solving the deepest mysteries of ocean chemistry, or finally cracking the code of complex biological systems, like finding those elusive, reliable biomarkers for devastating diseases like Alzheimer's. What discoveries are still waiting out there to be unlocked? Unlocked perhaps by this powerful tool, but maybe even more importantly, by us carrying forward that same spirit of cross-disciplinary exploration, that willingness to connect the seemingly unconnected that originally created it. What complex soups are you trying to understand in your own work, or maybe just in your own life? And what unexpected connections, what borrowed tools or ideas from seemingly unrelated areas might just help you find a better, more insightful way to measure their ingredients?
Definitely something to keep in mind as we all face new challenges and complex questions.
A fantastic thought to end on. Thanks so much for diving deep into this truly fascinating story with us today.